Okay, in this section of 2.8, we're going to talk about this concept of related rates. In the previous section, we were using the rate of change, which was the instantaneous rate of change or the growth rate. Now, what is a related rate? A related rate refers to a rate of change with respect to time. Which we'll see here, dx dt, dy dt, those are rates of change with respect to time. In differential calculus, related rate problems involve finding a rate at which a quantity changes by relating another quantity to others whose rates of change are known. The rate of change is usually with respect to time, high percentage of the time. So dx dt represents the rate of change of x with respect to time. dy dt represents the rate of change of y with respect to time. And during this COVID-19 pandemic, I got a few examples, right? A positive, LACC distributed 500 Chromebooks per week. On a not positive side, the pandemic, right? New York last week had 800 deaths per day, roughly. So if you look at your related rate, you have one quantity here that is changing per a unit of time. And this would be nice to come up with one of your own due to the pandemic here. So that'll be interesting. We could pair share when we get back to class. Now, when we're using our related rates, we may need to use one of our elementary geometric formulas. The area of a circle, the volume of a sphere, the volume of a cylinder, or a volume of a cone. And what's going to happen is this is in with respect to one variable. However, here you have two variables. So in a case like this, one of these has to be given, the radius of some sort or the height, because you could only take the derivative with respect to time. Take that back, because in this particular case, there is a chance where these may not be given, and you could take the derivative with respect to time, and you would actually have to use the product rule. So that is a possibility. Here are some steps that we want to make sure we are following when we solve a related rate. A related rate problem is going to be, i.e., a word problem. So sometimes you'll notice that it's helpful to draw a picture. Sometimes it's helpful to state what the variables are given and what rates of change are given. Sometimes it's helpful to state what is being asked. And then from that information of your drawing, you will need to state one of those geometric formulas. Once you have your geometric formula, we're going to find the derivative with respect to time. Then we're going to replace the given values to determine what is being asked. If the rate of change is positive, then that rate of change is increasing. If the rate of change is negative, then it is decreasing. So we never use negative values in our final answer. We will use the word increasing, or we would use the word decreasing. And then it's important that we write a sentence conclusion that contains units. A lot of times the units are not there, so I have to take off points, and we're going to state both exact and the approximated values. Rookie mistakes, right? Not knowing the correct formulas. If you don't know the correct formula, then everything is kind of shot to, it's problematic. Introducing specific values of our rates and our variables way too early, so you want to monitor that, and always remember to obtain a general formula that involves the rates of change at any particular time. Specific values should not be substituted for the variables until the final steps. So that's something that we want to take into consideration. And so if we go over here to, let's take a look here at this example. If the volume of a cube with edge length x and the cube expands as time passes, find dv dt in terms of dx dt. So what is that going to look like? Well, I'm not the best drawer, but let's kind of just take this real quick. And let's take a look here at a cube. So let's just take this cube here, and the cube has the same, let's take this Rubik's Cube here. The Rubik's Cube here is going to have the same length, the same width, and the same height. And if it's expanding, just imagine that Rubik's Cube is getting bigger, right? So when you're talking about a three-dimensional figure, what are we talking about? We're talking about its volume. So when you're talking about the volume here is going to equal x to the third power. And if we are finding dv dt, then we're going to take the derivative. So that's going to be dv dt, which is going to equal a 3x squared, but this is going to be dx, and this is going to be dt. And if they're asking us to find dv dt in terms of dv dx, I misspoke, yeah, dx dt, well, that's what this here is going to represent. And so this here, we did not need a formula. Oh, we did need the formula, sorry. We needed the volume of a cube. And then we'd had a figure. And what's going to happen is if we're not getting the formulas down and we're not getting the derivative down, then we're not going to be able to replace those unknowns. And then we'll pick up a little bit more of these examples during lecture. And that file that I gave you, we'll pick up from those examples later.